you all for coming to discussion hour. This week we're going to hear from I'm just going to introduce you guys as the Project Terminus team, because it sounds like this is going to be a fairly collaborative effort, so I'll let everyone introduce themselves as the presentation goes on. But just as a brief introduction, the Terminus Project is a multi-institutional collaboration between UT Austin, the University of Florida, Oregon State University, Rutgers University, and Woods Hole Oceanographic Institute. They embarked on a field season to Central West Greenland in August of 2024 to observe how sediments impact the stability of Greenland and of Greenland outlet glaciers. So we're going to hear from them about their trip, and we can't wait. Thanks.
All right, so I guess we can just begin. Kind of to the Terminus team, do we want to talk about the slides that each of us had created? Or
Yeah.
like I opened it and suddenly it's full. All right, so I guess beginning with the motivation of this project, like why are we exploring this region? Whoever made these.
Who are you?
Casey.
Who are you?
Oh, I'm Casey. I'm a grad student here. I work with Ginny and Benjamin. Yeah.
I'm Mikayla. I'm also a grad student working with Ginny and Benjamin. I was on this expedition.
I'm Ginny.
There's people on the owl. There's people on Zoom.
Okay.
And then,
So let me just quickly give a little bit of motivation for this project. So all these glaciers, this is a place for them to see. Here.
yes.
Okay, all these glaciers in Greenland show red circles indicating that they retreated, but the size of the circle is quite heterogeneous. Some glaciers retreating quite a lot, and other glaciers retreating very little. And then the blue circles indicate glaciers that have advanced. In addition, there's some glaciers that haven't retreated at all. So there's a lot of heterogeneity in the terminus position of glaciers in Greenland that also is seen in elevation change, which this is a complicated map showing, ignoring the color scales in the interior. Just looking at these dots, we see like a lot of different colored dots and symbols. Doesn't matter what they mean, it just means that there's a lot of variability in how the glaciers are individually responding to climate change. We know that the global climate has warmed and that glaciers are retreating, the ice sheet is retreating and generally thinning, but there's heterogeneity in the individual glacier response that has been like lacking understanding of a mechanism for driving that. Next slide, please. So this hypothesis was really come about from a model study that was done by Doug Berkerhoff, and this is his fancy result, which is this beautiful, simplistic model of how a glacier interacts with its bed. In this model, the ice surface is the cyan line, the dashed line is sea level, black is the bedrock, and then red is sediment. You can see over time that this black line is going down in elevation as it's eroding sediment and evacuating it out to the ocean. You can also see these kind of dramatic cycles back and forth of the terminus position, and that's simply the result of coupling the ice to the sediment substrate underneath it. That builds topography, this little bump that the glacier interacts with and creates some temporary stability that eventually it loses and then it retreats. And then this is the terminus position over time that is changing in a way that is completely outside of any climate forcing. The climate is held steady over this time. And so our idea is that while the overall driver of change in Greenland is mostly a climate signal, that this imposes some degree of heterogeneity that is yet unexplained. So we went there trying to understand, this is a model built for Alaskan systems, and we went there to try to understand how much could this be a role that's being played in big ice sheets where they are less wet, they're less steep, so they probably have less sedimentation happening, but it could be something that's helping to explain some of the heterogeneity that we see. I don't know what's next. We can skip this one. Oh yeah, so I wrote this little Instagram post. I thought this was cute. So I look at satellite images like this all the time. And so, you know, when we think about glaciers, when I think about glaciers, I think about them at these scales. But then if you go to the next slide, and then the next slide, we're getting closer and closer. You start to see these individual. Oh,
sorry. What?
Go back. Go back. Okay, so you start to see the individual pixels that make up the glacier, and this is actually our ship in the water that was taken while we were there. So if you go one more, that's like our ship is like 1, 2, 3, 4, 5, 7 pixels across. And then the next picture, I think, is a little movie that actually shows you the resolution, of the actual ship, what you see with your eyes. And so it's kind of remarkable to go from a place that you see it in terms of these pixels, which really don't define the scope of detail that you could actually see when you're there live in person. So it's kind of just a way to show how, we take things with a grain of salt at the satellite scale, but there's so much happening at this observational scale. It's really critical. I don't know what's after this. I'm not done.
Just watching it again, because no.
This is also drone footage that Casey. So I don't know who's next.
I did the next few slides, so we'll go through a little bit about the Celtic, life on the Celtic, and then we'll get into some of the science, of course, which is very exciting. So this is the second half of the cruise pulling up to the Celtic. And actually, before we even get to Cass, we actually started in Galway. So a few of our PIs, Sean there and John Yeager at University of Florida, flew into Ireland to also dock the ship with the rest of the crew to put in our equipment. There's Nui, oh yeah, Woods Hole also boarded around this time, and they took about, I think, what was it, like a 10 to 14 day trip to get to
7.
Oh, never mind, 7. Just 7 on the open waters. So yeah, there they are, putting in some of the equipment. We see Nui, we see some of the larger containers that we do some of our analysis in. Here is, I was trying to show what was happening on one of the main decks. We have our wet lab that's there in the upper left, where we did a lot of our sediment analysis and drawing, also a lot of setup for the submersible team, also the oceanography team setting up things. Here's some of the crew helping with things on deck. There are also a lot of machinery that they operate that was going on. This is where everyone was hanging out. There was a cute picture of everyone on their phones drinking coffee, but I was just like, I don't know how appropriate that is. But anyway, it was fun. It was fun hanging out in this little alleyway with them. And then here's the food. I heard from another PI that was on the same cruise like in 2023, and she was just like, be careful with the food. I showed up and I was like, this is the greatest thing ever. Tony and Paul, love them. They provided so much food for us every day. That kept us going. And it was lovely. That was happening on the main floor. On the third deck, we have I'm forgetting all the names.
Patty.
Yeah, well, there's Patty. He was one of the 3 captains. All the like terminologies like losing my brain. Yeah.
Captain, first mate.
Yeah, I don't remember if he's the second mate or the third mate.
He's
the second. So Lauren here, but he was pretty funny to hang out with. And then this is like some of the views that you would see from their deck, and also nice imagery of the back of the boat. And then here's where all the fun stuff was happening. We have a picture of the bow where all the drone stuff was taking place. We have a little science meeting room where we talk about data. And then this was like the main cabin that we were all hanging out in. You can see that there's like a ton of monitors that people spend trying to put up and kind of log things. And so this is where we spent the bulk of our time. I don't think anyone took any images of the rooms that we were in or other parts of it, but it was nice. We had like a full gym. There's a sauna. I know Benjamin can speak to some of that. It was really nice. And then full laundry. Great. Celtic Explorer, high ratings for all of them. We had such a great time. And then Life at Sea, there was a lot of teeth. It's very Irish and just like a lot of the men on the crew. They're so funny, so sweet. And there was like a little feud going on between the 2 T's from different parts of Ireland, and they were a little judgmental on which one you would pick. Does anyone have a preference that they had when they were drinking this tea?
Yeah, berries.
Berries.
By far the best.
Well, that was that. And then we always had soup for lunch. I always looked forward to it every day. Soup and salad. Tony took a lot of pride. No, Paul took a lot of pride in his salads. So yeah, and then a cute little sunset. So yeah, we're gonna get into a little bit of the science, and here are the different teams. We have a plume oceanography team that's based out of Rutgers and now Tufts University. And here is the PI leading and also co-PI with some graduate students. The sediment slash core team that's looking at sediment observations and turbidity. And so our two PIs, John Yeager at University of Florida, Emily Idam at Oregon State University, grad students, our lovely tech Dan that y'all are familiar with. Sean, John Goff, Pear and Dallas also leading, Johnny Mandola, and Marcy, part of the screen blocking. Sure. Maybe the noises. Part of the geophysics team. And then we also have the glaciology drone slash modeling team for all things related to ice. Here is the NUI team that operated the submersible, led by Molly and other engineers, and of course our logistical and financial team here at UTIG. Without any of their help, none of this would have happened. And Kara, shout out to our girl, because she helped the second half of us trying to get out of a lot of flight situations that we experienced. So yeah, what's next? Okay, so a quick what happens in 24 hours. We had two big shifts going on, at least for the science team. We had midnight shift to noon, and what was happening at, well, it wasn't exactly at 12 a.m. It was like around 11:50, 11:45. We'd maybe meet, we'd chat, be like, hey, like this is what happened like during the day. Here's like our plan for the night. And so we see Sean writing down some things. And usually what's happening in the night shift is coring, anything geophysics seismic. And here we are setting up a gravity core. Here's an image of us deploying some of the seismic stuff, and Dallas working very hard to get it
out. That our seismic tech was delayed in arriving because of the death in the family, and then arrived with COVID and left like 2 days afterwards. And Dallas really rose to the occasion and learned over the phone, I think.
Yes, you sent copious notes, yes.
Yeah, I mean, it was pretty amazing to see her go from like not really ever doing this before to like fully taking on that responsibility. So really
Clearly upset with something.
Yeah, big shout out Dallas. It was a lot of like deck talk going back and forth and people running in and out with like a bunch of gear on. And so yeah, it was awesome pulling this all together with the shorthanded team. And then sediment stuff was going on at night, drying samples, writing them up to make little vials that we can test later, and then also a lot of calibration for the list and other turbidity instruments that we put on our submersible. So that's what's going on in the night shift. What's next? Here's some fun images put in about how, yes, we are in high latitudes, but the sun is also out when we're working late at night. Unless it was super gloomy, then it was pretty dark. But this is what the night shift actually looks like. Pretty bright and high spirits with a thumbs up from John. And then it starts the 12 p.m. to 12 a.m. shift. We do another team meeting where we talk about what happened in the night shift, what's going to happen in the day shift, and a little bit of conversation passed in between. And then the oceanography team takes over. Here we are prepping for a CTD cast. The drone team. I don't know which one this is. I don't know if it's which bird.
I'm trying to see if there's any like writing. The writing in red is tern.
What's the other drone's name? We named the drones after Greenland birds.
Yeah, like Arctic birds. So there's tern and kittiwake. I don't know which one that is. I can't see the writing on it. But if there's like a green piece of green writing, it might be kittiwake.
But what does matter is that over the course of the 4 weeks-ish that we were there, the drones flew a total of some 1,500 kilometers, which is like enough to fly across the ice sheet and back. It's pretty remarkable amount of output from those little machines. I was impressed.
They're putting in
They
overtime.
were the sleeper star of the whole cruise, I would say, because we brought them as a last minute addition, and they were heavily relied upon for reconnaissance, which was not anticipated. And then and the team rose to that occasion. And then they were also really valuable for just glaciological observations, still to be determined.
Were they just taking photos or video, or what kind of?
So yeah, orthomosaics that will hopefully turn into nice DEMs. So one real big challenge is there's no ground control. We're on a boat. There's no way to put out GPS anywhere. So we've come up with these like imaginative solutions for hopefully correcting these to make DEMs that are actually referenced. But it is definitely stretching the limits of like what's found in the literature. So if anyone has ideas, we're using like ISAT to try to do this, but then also ISAT doesn't have a lot of points in the middle of the glacier where we're surveying. And so yeah, we're open to other ideas on how to get some ground control for these, but we have a really awesome undergrad who's going to be working on that this semester.
I think we have a total of something like on the order of 30 orthomosaic DEMs, so like X, Y, Z reconstructions of the glacier of like 30 times through the course of a month. And when we were there were a couple really big calving events too. So relative to one another, we have a lot of information to reconstruct how the glacier was moving and stretching prior to when some of those big calving events happened.
I think we have some, do we have any images of the drone?
Yeah, we're gonna get to the drone section, I think in 2 slides. I think there's one more of this. Yeah, and then what's also happening during the shift is the submersible team. Yeah, so this is Nereid under ice. We're just gonna keep saying Nui. And this is Victor, the main pilot, with the Xbox 360 control here, controlling Nereid, but we're gonna get into that now.
All right, so as kind of Ginny and Benjamin were just talking about, we brought 2 drones, and they were here to survey the terminus face, but we also use these to survey ice conditions for the ship, for some of like, for Nui, for X-Ocean, which collected some bathymetry data. And so you can see the little drone up here in the top left, and this is kind of the team that was doing a lot of surveying in the second half, which was Marcy and Benjamin, and then Marcy and I collected a lot of stuff in the first half, and Dan as well was helping to collect. And so, yeah, we're really looking to just capture these changes in terminus position throughout time with these drones, but also they're very valuable in capturing what the sediment plume was doing. And so here are just some rough reconstructions that we did on the ship. So we have a couple of products out of the drone and the photogrammetry work that we did. So the first one, as you can see on the left, are these 2D orthomosaics that kind of just stitch all of the photos together to get a more accurate like terminus position. And we ended up doing this almost on a daily basis. And that would go into some of the navigation equipment, like you see here for Nui, just so they know, like, just so they have like the most up-to-date kind of position possible for the terminus as they're going along and scanning it and collecting samples nearby. And then another thing that we can do is create these digital surface models. And so like Ginny was saying, this like collects X, Y, and Z data. And so we can get these like rough maps of like some of the crevasses and like how high the terminus is in certain areas. And so a lot of this kind of like preliminary data was just to give us like a good idea of like, are we getting enough photos to stitch them together and to create actual models. And so we're going to be going through and reprocessing like all the runs that we did at a more like accurate and higher resolution in the future.
Well, one thing that we decided to do with that was to take the terminus line that's available in the digital surface model that's there, and that line is the ocean surface, and so that actually gives us this kind of pseudo ground control if we assume that that's at 0 at sea level, or what the geoid is in this location. And so that's one way that we're going to try to see if we can do it referencing.
So the surface height is relative to that.
Yeah.
And then these are just some fun photos from the reconnaissance stuff. I personally, like, when we did reconnaissance, sometimes it was kind of a pain. But also you get to see like just like these really beautiful ice conditions sometimes. And so this top photo was looking down into the fjord as we're coming in from like the ocean waters into the fjord. The boat at the very beginning of the cruise was very hesitant to get anywhere near any sort of ice. And so as we were pulling up to the fjord, they were like, can you fly closer to see if like there are any large icebergs in the way. So it was kind of fun to get to use the drone for that. The ship eventually became very comfortable with being closer to the glacier and closer to like kind of larger icebergs. And so we were able to navigate closer and closer to the terminus face. But this is also a snapshot from a reconnaissance mission. I think this one was just to look at ice conditions for X-Ocean. And then you can kind of see a little bit of the plume down here. I don't know if I had included any plume photos. I was trying to get a video of it up here, but it was like taking too long to download. But anyway, yeah, this is kind of our.
If you would like to see
Yeah.
plume videos, stop by the pod.
Yeah,
Now on one of our televisions, there's a loop that will play with a number of videos that were taken from the drone during the expedition.
I also
grab some media and watch videos.
Yeah, I have it pulled up on Fox as well, so maybe at the very end we can just like look at some videos from it. Yeah, from the drone you could see like a lot of detail within the plume. One of the people or the ocean PI from Rutgers was talking about how it kind of like boils almost. So we have like this water that's full of sediment that's exiting the plume or exiting the terminus face and creates this like plume right at the very edge of the glacier, and it's like very dynamic, and it's like it does look like it's boiling. And so I think a lot of animals like sea life are in there. And so you get fun little creatures like seals playing around in the plume. So we have videos of that and birds hanging out. Yeah.
You want me to talk about NUI?
Yeah.
Sure.
So the big star of the show was the use of NUI, which is an area under ice. It was built for being underneath ice, and it's never been tested in a terminus environment. It's always been used in sea ice conditions. So this was a new, I mean, it was built for this, but it was never used in this way. And there's risk associated with the use of NUI because it's a very expensive, a lot of development went into developing NUI that we're then putting it into a very dangerous situation. And so it's inherently just risky, but the Keck Foundation loves that stuff. And so they funded this. And the thing that we loved about NUI was that it's not only like a geophysical tool, so it does a ton of mapping and observing as it's moving around, but it has this bay that opens up and a sampling arm comes out. So it can also simultaneously sample on the seafloor, grab samples and all that kind of stuff, and then store them in this ridiculous and simple milk carton. And it's all operated via a fiber optic spool, which says 20 kilometers, but nominally in this environment it was only 3 kilometers. And so it's literally connected via a fiber optic cable 3 kilometers. This thing is traversing like all over, and it only broke one time. I think it only broke one time, and then they have a pre-programmed like automatic route that it can do a whole bunch of autonomous mapping, even though it's broken. So there's still like tons of data that can be collected, even if it's not being like manipulated in near time. So the fiber allows the transmission back to the ship for all of the information, like all these cameras, all the data coming back, so we can see in real time what NUI is sensing, which is really amazing. I don't know, what's next?
Does it have to exactly backtrack the way it came to like spool the fiber?
No, it leaves the fiber behind, but it has to, like, the fiber settles in the ocean slowly. And so it has to make sure that it doesn't cross over the fiber again, it doesn't get tangled up. And so if we're asking it to go back and map a second time, which we had done at a higher elevation or something, we had to be strategic about making sure we were doing that so it didn't get tangled. Yeah, we left like 7 spools of fiber just like on the seafloor. Yeah, sorry.
I think this is the video.
Oh yeah, so one of the amazing things that I really enjoyed seeing with NUI was the multi-data, and maybe, I don't know if you can like stop this.
Yeah.
And
would you like me to go
through what we're seeing, but, so NUI had a multi-beam that was forward-looking that is used primarily for navigation, so it doesn't hit obstacles. Because it doesn't have eyes like seeing forward. I mean, you could put a camera on there, but in this environment, you can't see like your hands in front of your face. And so it has this multi-beam for looking for obstacles, and then it has a more flexible multi-beam that is either pointed down the seafloor, or we mounted it sideways to point at the ice face. And so we mapped the terminus of the ice face And the novelty here was being very close to the ice face and also being very close to the grounding line where the ice is meeting the sediment. And so we flew NUI at two heights along the face. One was 25 meters and then one was 100 meters. And I think this was the 100-meter one. This is the path of NUI. And then what we normally looked at was just the beam return. So just like a single beam of this, but then on the fly, the NUI team, who was amazing, coded this up to be able to record like 10 minutes or so of these points being added up. So we could actually kind of look at what the face looked like as we're recording data. So Dan is like busy cleaning all of this. So I don't have any like really nice data to show you, but this was just like taken with my iPhone of this cave underneath at the terminus. This is the ice wall and the sea floor. And this was a cave that's like 70 meters across and about 100 and something meters tall that NUI passes over, and the beams are just like lost in this, so you can play that. And we also did some cool experiments because NUI also has upwards and downwards ADCPs. And so near the end of the cruise, you can play it.
Okay.
NUI team were getting more comfortable being in this environment, if you want to replay it. So these caves are subglacial outlets, and there's like a ton of fresh water being pumped out of these outlets. And because there's a lot of fresh water coming out, it's buoyant, it rises directly above here and melts the roof, and it's inhaling warm water at depth. So there's all this water from the ocean that's trying to get into that, and then it's being entrained and rising upwards. As NUI's being piloted in there, the pilot's like, oh, I can feel it pulling me in. And he had to kind of keep balancing to keep from being pulled in. And then at the end of the cruise, they actually parked NUI inside of this with the upwards and downwards ATP to measure the velocity profile in the cave, which was pretty fun to see. There might be another, if you want to advance this, there might be another. You can advance it. There we go. This was another one that I really love. This was NUI flying 25 meters above the bed. Again, this is the bed, and that's the glacier. This was the most remarkably flat part of the terminus. And this down here is a gap that we couldn't see the back of this gap. And so my hypothesis is that this is a place where water is leaking out rather than being a discrete channel. It's like a distributed system here, which is kind of expected for glaciers, but we never really observed it. And so it's rising buoyantly still and creating this kind of more uniform, flat face of the terminus in this area. And I don't know if there's like iceberg pics after this. Oh, this.
Yeah. I was gonna say,
sorry,
like,
I was getting in front of it. So this horrible picture actually is an iceberg that calved off. So it was attached to the terminus. The face of the iceberg moved off the glacier and then fell like that. So it was exposed at the surface, and we flew the drone over it and captured what the terminus, the submarine terminus, looks like after it calved off to have a picture of what this could look like. And maybe you can make out, this is actually 200 meters tall. The ice is 300 meters tall. So it's like the majority of the terminus space. You might be able to make out these ridges. I don't know if you can see those.
Should I make?
There's a high quality.
Is that her?
Oh, okay, great. So these ridges here are perhaps a signature of melt. They actually come up and branch a little bit. The top of the glacier is here, bottom of the glacier is here. And I think that this could be a signature of that kind of leakage of water that's coming out. There's also a 40-meter debris layer that's frozen onto the base of this iceberg, which is really informative as well. And that might be all I have up there. Yeah.
Okay. Okay, so this is the marine geophysics section. This is mostly what we were doing on the night shift. And so we weren't looking at the glacier itself directly. We were looking to image the subsurface to learn something about the sedimentation rate and kind of volume of sediment the glaciers put out historically, and that kind of thing. I'm more of a tech person, so I'm mostly just processing the data, and I've gathered some vague idea of what we were doing, but that's really John Amendahl's problem. So yeah, so this is just a map of all of the lines of seismic and or shipboard chirp we collected. I'm going to show you a process, seismic line, kind of coming all up and down the Caspian. We spent most of our time here. This is the glacier we were just looking at. And then we briefly went over to this glacier, this as well. I forget exactly how many line kilometers of data it is, but it's a lot. Okay, you may go to the next slide. So, okay, so the most fun part, I thought, was the multi-channel seismic data collection. This consists of a GI air gun as the source, and then, which is this guy here. This is the air gun, and it's towed under this giant float with a GPS on top. And then behind it is this 300-meter long streamer that has 88 hydrophone locations. And so this is the multi-channel seismic reflection. So we're getting bounce backs from like impedance contrasts in the subsurface, right? This is just a picture of us deploying that streamer. We were unfortunately only able to use this like 3 times over the whole month because there was quite a bit of ice around. And when you have 300, something like 350, 400 meters behind you, and only a few kilometers of width in the fjord, and it's full of ice, you lose ground pretty fast. So yeah, okay, next slide. Yeah, so this is the internal computer setup. And this is one of the processed sections. It hasn't been migrated yet, so you can see a lot of the kind of U refractors that we'll eventually get rid of. But so this is kind of the whole fjord. So you can see these like flat, perfectly horizontal kind of layering bits. That's where you've had the sedimentation, right? And after it was submerged with seawater, right? And then this impedance contrast here, this is going to be an old moraine. So kind of that video Jimmy showed at the beginning, where you kind of get that undulating bottom feature. That's kind of what we're seeing here. So these are different points where the terminus of the glacier sat and like created a terminal moraine. And now, of course, it's retreated way back up here. And there's been sedimentation on top of that. So that was a really nice image to come through. And then just some pictures of our shot together. So this is what we were looking at on the screens when the data came in. And that's where the air gun in the water. We took the tail buoy off the end of the streamer so it wouldn't like run into ice and try to drag it with us. Okay, next chart. Slide. So the vast majority of the data we collected was the shipboard chirp data. So this was mounted on the ship's hull, and we more or less had it turned on whenever we were moving. It was Marcy's favorite thing in the whole world.
It actually makes a sound.
Yeah, you can hear it. And one of the great things about the Project Explorer is that it's electric diesel and it's designed to be really, really quiet. So it's by far the quietest boat I've ever been on. So in the like dead silence of the boat, there's this really loud, obnoxious chirp sound going all the time. And so this is what we were using. We were processing this data on board, and we were using it to pick out coring locations. So this is the kind of command center. It has the shipboard chirp coming in, it has the bathymetry screens coming in. We could see the map that's up on the bridge, and this is where we did all of our logging. And so this is just also a photo taken from my iPhone when we were looking at, we wanted to get a core on some of these like nice sediment waves. And so we were zooming in to try to find a GPS location like on top of one of those little mounds to drop a core. Next. So these are a few select lines from the shipboard chart. and a zoom in of all of our trip lines, it looks like spaghetti, and there's a very good reason for that. And that reason is also ice. So, you know, you pick a trajectory and then you go around it. And then where you see gaps are where there were like huge icebergs that were just kind of there the whole time. So this is also a map of continuous ice presence. So we have two lines that are like perpendicular to the terminus and one that's parallel. You can kind of see the nice plateau that's up closer to the terminus, and then this drop off into the kind of deeper basin. That's so some of the things we're looking for here, like the nice planar layering of like sedimentation, and then this is kind of blocking it. But where you don't have those, and you can kind of see like gravity flows where stuff just kind of slumped down and there's no order to it. And I think that's something John is interested in. Okay, next. Yeah, so coring, we have 3 different kinds of cores. The multi-core, which I think like a handful of times we got a successful sample from. The ground was just really, really soft, we think, in a lot of areas. And so the multi-core just wouldn't trigger. We would just send it down and we would just get water back. So I think we eventually gave up on it, and John Yeager jury-rigged his piston core to be a small gravity core. So that's I think 2.5 inches diameter and 3 meters in length. And that's what we use the most for coring. And then we also have the jumbo gravity core, which is like 4 inches in diameter and 6 meters length. And so John was really interested in preserving the like water sediment interface, and he's looking for what kind of layers he can date to get a sedimentation rate for us. And then between the cores and the seismic, they'll put together a kind of sediment volume estimate kind of thing. Okay, next. Right. So obviously not all of the ground was really soft, only some places. And in one of the not soft places, they dropped the jumbo core quite hard, and it bent. But don't worry, we had like 3 more, so we were able to get more cores after this, but not with this particular barrel. And then here are just some examples of the small gravity core. You know, sometimes they're full at the top, and sometimes there's like 4 inches of sediment and water. Okay, next. Mikayla, what on earth were you doing in this saddle up on the boat?
So one of the containers on the Celtic we borrowed from the Marson lab at Oregon State. They pretty much contract you these containers where you can do your analysis on board. And so we were able to get we were able to x-ray. So after the image that Kyle just showed of everything just kind of sitting there and settling out, we pulled them into this container, let them to continue to settle out if there's a bunch of water, just so we can preserve the export interface. And we x-rayed them. This is like a little x-ray box. You're supposed to get out of the room apparently as someone pushed the button, but who knows, maybe those x-ray rays will get to me someday. And then here we have a core logger, which we were getting like the magnetic properties out of the core and kind of log that and process it later to understand what is happening within these different layers, and that can tell us something about the deposition over time. So we spent a lot of time in here, kind of pushing cores through here. John did a lot of this x-ray stuff because he's certified to do that. And these are the different parts of that core logger to get, the magnetic properties. And we were able to get some graph samples in places where the core wasn't working. It was such a bad game that we were playing over time. We were just sitting on the deck and we were like, do you think we're gonna get anything? And yeah. And they're like, if you're wrong, you owe me a beer. There was a lot of beers at the end of it that were still like, but anyway,
are you mashing it with a fork?
This one?
Picture.
Do you mean the sediment sampling device?
I think that was like the dining hall spoon. Get that like nice layer or something. Was it you, Benjamin, getting this one? I think you got a couple. That's right, John. Okay, next slide. And then, yeah, so some of the successful multi-cores we had to let sit out over a few days before we started extruding them, which is basically like sampling every like inch or centimeter until we hit like the really goopy stuff. And so we dried those samples up, and these are what are going to be dated to tell us like what's the most recent deposition of these sediments. That's all I know about sedimentology. Do not ask me what what chemistry.
Is that NUI also captured cores really close to the terminus, so probably I think they are the closest samples taken, closest to a glacier. And part of that is to get material for dating, but also grain size, so that we have some basic of, for putting into models. And NUI also had a chirp on board, which is like incredibly high resolution, very close to the seafloor. What?
So we have a slide about that.
Oh, okay. Yeah, so there's like a whole bunch of other data too.
Yes.
Yeah. So
I have a quick question.
Yeah.
What does a multi-core do that the other core is gonna do? And why didn't it work?
It preserves the water sediment layer the best out of all of those cores.
Especially since the bottom is soft, a lot of times like that, you saw the stack of like giant yellow weights on top of the large gravity core. It'll like over penetrate, and so you're actually getting like meters 1 or 2 through like 7 or 8 instead of the top bit. So the multi-core gets the top bit. But yes, good question.
It was very soupy seafloor. It was very ill-defined.
Yeah.
There's a lot of mobile sediment at the bottom, and so it just like
It would just
kept
slip
going
through.
through all the time.
Yeah.
Just want to know where the bed was.
A lot of times the cores would come back just like the top part covered in mud, and you're like, no. The core barrel's supposed to be covered in mud.
There was also one unexpected sampling of sediment where NUI was trying to core and being really unsuccessful because it couldn't see anything. All the visibility was gone. And then when they tried to get buoyancy and come back to the surface, they could not get buoyancy because they had taken on 50 kilograms, 100 pounds of sediment in like 30 minutes or something like that. Because there was so much sediment in the environment. And so they had to release these emergency ways to get buoyancy and come back. Which is pretty amazing. So we got a lot of sediment just from NUI in the day.
And I did use a kitchen spoon to sample that.
Yeah. That's the one. Yeah. But yeah, we let those dry up in the oven, and then I mashed them up, and I put them in these little vials that I concentrate them with mucose for. Next slide.
So another component of this was bathymetry. Again, we had 2 shipboard multi-beams at different frequencies. So we had the 420 was the higher resolution one that we turn on when we were in like less than 300 meters of water to get the really high resolution stuff. I think that's this one. And then this one was lower frequency, so you could see deeper, but also much less resolved. So we had that one on most of the time. And we also had the backscatter turned on. And so I think this was one side of like one of the main channels kind of on the plateau near the terminus. And there were a ton of these little like rivulet features, which I'm really interested in. So apparently it's interesting. And tells him something important. How are we doing on time? 10 minutes. Yeah. All right. Listen, I was just wondering how long of a rant I would go on. We can skip it. Okay, next slide. Yeah, so then the last bit of this kind of geophysics information did come from NUI. NUI also has a multi-beam, so we're going to get coverage near the terminus from that. And it also had chirp that they put on NUI for us. That's not something that NUI normally does. So they added this chirp for us. So this is just a couple shots I think Sean took as the data was coming in real time. And so as Jenny said, it's just very, very high resolution, very close to the seafloor, and much, much closer to the terminus than the ship would have been able to get. So that is very exciting. I'm working on processing that. Yeah. And I think that's the end of the range of
So no one here at UT was on the oceanography team. But a quick shout out to what they were doing, and what they were collecting. They had a ADCP collecting from the ship itself, but also on NUI. And so there's a lot of cool data showing the velocity that's coming out of those subglacial channels. And there's Bridget in the hard hat on the right, who's a grad student at Rutgers University, kind of calibrating the CTD, which they do like multiple casts like throughout the day just to get that like daily resolution. There was also, I don't have an image of this, but I was walking around late at night, and there was like a fishing pole in the back, and I was just like, what is that? And they're like, oh, like the CTD's attached to it. So we were like going across the fjord, getting like CTDs and other data.
Yo-yo CTD. So
Yeah.
It just goes up and down as you're traversing.
I was like, what? Who's fishing back there? And they're like, we're not fishing. And I was like, okay. But yeah, and then there we are on the left-hand side, looking at some of those CTD casts that they were doing stationary. So yeah, shout out oceanography team. Okay, I think this is some of the data you put in.
So I think if you wanna go, yeah, so this is just like some of the multi-beam data to show you sort of the added benefit of having NUI. So this is just like a Google image of the region. You add in the next slide. This is our nice orthomosaic collected from drones. So I'm not going to zoom in, but like the detail is pretty incredible. You can resolve individual crevasses and fractures and all kinds of beautiful things. And then the next slide, so this, I just marked the terminus position with a line so that we can remember it and not have the glacier here so we can see the data in all of its glory. This is the shipboard bathymetry that was collected, and it's out of range, the color map, because I am gonna load on the NUI data on top and the color scales match. And then the next slide, I think, has NUI data to show you how much closer that we got with NUI. And then hopefully, what you can see here, so the NUI data is laid on top of this ortho mosaic. And so you see how the terminus is ahead of the edge of the bathymetry. So that means that NUI was able to see underneath the terminus, like in many of these locations. This is the big cave feature that we identified. And then there's a bit of a gap here because there was this persistent iceberg that was there pretty much the whole time that we were there. And then the next slide. Oh yeah, so what I wanted to draw your attention to are these like radiating channels that you might be able to see that are really nice, effective evacuators of sediment, we think, from the whole glacier. And we think that they're radiating towards this larger channel that's delivering sediment from this upper plateau to this lower plateau. The next slide. I think you can start to resolve in here, maybe some of these channels and how they connect. And then I don't know if I have another one, but okay, so blow up. I did this a couple, like a week ago. Okay, what's the next slide after this? Removing the terminus, and then okay. So I did the hillshade on this, and it shows up better on my computer than on this TV screen. But what you're able to see, hopefully, are bed forms in the multi-beam data. That is remarkably similar to some of the data we saw from Brandon Carlson's talk last week. Suggesting that there's a tremendous amount of diffusion of sediment away from the terminus, and that the moraine may actually be kind of in a steady state because the glacier terminus this is a glacier that hasn't retreated, I should have told you that at the beginning. So over the satellite era, it's experiencing seasonal change, but the overall terminus position is quite steady. And so that probably means that the moraine also is in somewhat steady state. And there's a huge volume of sediment coming out via different mechanisms, but that sediment is very rapidly being evacuated from the system. And then I don't think I have it, but we did go to this area. Marcy and Dan went in 2013 and survey with multi-beam very close to the terminus with a boat captain that was very courageous. And the channels that you see here are in the same location as they were in 2013. So these are pretty long-lived features, and we think that the moraine, first pass of this moraine is like pretty steady state kind of system. I think that's all the preliminary stuff I have. Yeah.
One more request and a question. Can we turn off the lights and go back through this last couple of slides, just like see maybe a little contrast? because they were beautiful.
I can also show you on the computer if you're interested. So we're hoping to do some bed form analysis to try to understand the flux that's happening to drive those bed forms. And then also this weird, so we kind of ignored a lot with what was happening in the middle because we were unable to go like right in front of the terminus in this area because the iceberg was in the way. But there is this, really unusual giant bullseye feature that I've kind of ignored. It has like a sinusoidal kind of channel evacuating from it. And that's a very long-lived feature as well. It was there in 2013 as well. Most of the water is actually draining in the center, which kind of makes sense with the hydraulic potential. There's like huge sediment plumes that are emerging from the central area. But it turns out that there's big plumes available in like around the whole, I would say like 6 maybe total across the whole terminus. And then this leakage as well of water.
So is that a cave that you were kind of, is that like a channel, like an art channel? Or
yeah.
Is it like, is there one or multiple, you said there's multiple?
I think there's like 6 of them and they were actually also in the same location. Like because Marcy Dan went there in 2013, they mapped the terminus and we could see these holes in 2013 and I was like, when Nui was like, where should we go? I was like, well, I think there might be channels here and here and here based on 2013. They were in the same place. Yeah. Which makes sense. The glacier geometry hasn't changed. So the hydropotential shouldn't change. So it kind of makes sense, but it's sort of remarkable how steady it is.
Sure, yeah.
The one downside of Nui, I'll just fill the hole. Is Nui is like operating underwater, right, in this murky environment connected with a fiber optic, and it has positioning via dead reckoning, which I don't know that much about. Maybe Marcy or someone else, Stella's might know more about.
Distance is speed times time.
Okay, and so it's just like relative to the ship, the accuracy is 20 meters, which isn't great. And so we could see so we had this one survey, Nui passed the terminus at 25 meters altitude and then went back and resurveyed at 100 meters. And when we see the terminus faces, they're offset, right? And so there's a lot of uncertainty that we see where the Nui has repeated itself and there's the data are offset. And so what we're planning to do is to have this nerd on the Nui team who's really excited to do this. It's like an optimization problem to take all the data that we've collected and optimize the position for correcting all of that information. And then we get an updated navigation file that then trickles down to all the oceanographic data, all the multi-beam data, all the geophysical data that Nui produced. And so that is going to take some time. And so I think by probably more like the end of spring term, we ought to have updated nav data that will improve all the positioning of our other data. And then we can really start talking about fine scale differences by summer or so. But the other kind of complicated thing was the way that, and I'm not an oceanographer, but the way that the ADCP measurements were made are also out of the norm. We had Nui go up to the terminus and we had an ADCP has 5 beams. And we had it just sitting there at the terminus, within where the beam could hit. You could see the ice face in the beam hitting and just recording data in that space. And that's an unusual application of ADCP data. And so they're working with the manufacturer to kind of understand how to unpack that and make sense of what the ice or what the water velocities were in between Nui and the ice face as well. So there's a lot of sort of and drone, using sea level for correcting our lack of ground control. There's a lot of sort of weird novel data processing that we're having to kind of pioneer in order to make really accurate observations from this. And that is kind of the boring part that's happening over kind of roughly the next year. And then hopefully we'll get some cool results out of that.
The turbidity was also, I heard, insanely high compared to the lab calibration. So they're gonna have to go back and recalibrate all of the lists because there's just this is such a high concentration that we've never seen before.
Yeah, we really underestimated how opaque the water was. There was an experiment we thought we would put out a sediment trap. So we put out this instrument and then we would go back and pick it up. and it would visibly be able to see them. And there was just like, you open the bay and it was black. And then we ended up putting on the bay walls, we put these markers, like a scale marker that you also couldn't see, like even just like that distance, you couldn't see. And so you can imagine, and there's a good article that was published on the cruise where they quoted the operator of Nui saying it was like when he was doing coring, it was like he was doing origami in the back of a moving car in a snowstorm. It's like black, and imagine being blind and you have an arm that you can only feel where this robot arm is penetrating a very liquid seafloor surface. So they did this approach, this was all like developed on the fly, where they rose above the seafloor surface and then descended very slowly with the arm out with the core barrel in the arm, and then like penetrated the seafloor and then came back up to a place where it was more visible. Instead of it's like falling out of the core barrel, and then they like try to put it back in the core barrel in a place where it's like slightly more visible. Like it was all very, we had to overcome a lot of observational challenges, I would say.
When you say feel, is there like haptic feedback or controls? No.
Yeah.
Yeah, we had like an Xbox controller for the navigation, but then the robotic arm, they had this like small model of the robotic arm that he manipulated like in real time, and that had some kind of haptic feedback. I mean, the putting away, each one of those little cores, like the hand of Nui was these like sort of 3 prongs, and then each of the cores had a little T on the top, and it had its own individual quiver that was not that much bigger than the core diameter. So imagine he's like kilometers away with this metal arm, picking it up with the 3 fingers, and then having to put it back. And he would try to get it. There would be happenings, but I mean, you could sort of see, but he was trying to basically like feel his way. It's like the needle in a haystack. It's like trying to put a core inside a core barrel from 3 kilometers away at the front of a glacier. It's like the new needle in a haystack. And he did it incredible. Yeah, we got 6 cores. Yeah.
Very impressive.
The most high stakes crane game ever.
Most high stakes, there was a lot of high stakes. I will say that we discovered that the drone data was really useful for Nui. They wanted to know like exactly where ice was so that they didn't break the optical cord. But sometimes the drone processing took a while. And there was one morning when Nui was going to go to the south side of the glacier, and we got up early so that we could fly a drone survey because there was a lot of ice material. They wanted to know where it was, and the processing software was taking a while to run the working with it. But they, knew we could only operate during the day shift from 12 to midnight, and every hour that they lost was like time that they could be out there. And so come like 1 p.m., we gave them, they had already been delayed enough, we gave them sort of the best image that we had. They thought, that's fine, we'll just launch with that. And we were standing out on the bow and doing more drone surveys, and they were just getting Nui in the water. And all of a sudden, this really big iceberg.
That one that I showed a picture.
The one that Jenny showed a picture of, it was 16 acres in XY space, half of the UT campus. Just broke off and it flipped. And the captain on board was, we have a video when it was happening, and it's like, I'm like freaking out. He was stupid. Dan like lands the drone, and you can hear the captain on the radio be like, well, I called the captain and I'm like, hey, Patty, we're landing the drone. And he's like, I don't care about the drone. I care about that like $1 million anchor that we're about to put in the water. That's called Nui. And so he calls them to get it up, and it all worked out. But we were then debriefing later. And if they hadn't waited that hour for us to produce the image, Nui probably would have been right there and been just like flung out of the air. And so the software's not faster. So it's a good thing that the software is so slow, or the universe is looking out for us that day. And Molly, the chief engineer for our cruise, she said, I'm glad it didn't happen, but I've always imagined that if Nui was going to go out, it would be in some spectacular fashion. And that's when I knew they took the whole like high risk, high reward thing really serious. We're on the same page about what it's like to work in this environment.
There's only one like end game for those under ice submersibles. Eventually, they're all gonna just end up just killed by ice. That's particularly.
Well, they're like getting rid of Nui, like, right?
Well,
Aren't they like
repurposing.
they're gutting it or something? Yeah.
But I think it's always available. If
Okay.
people want to use it. It's actually really underused, and so if people have a use for it, they're looking for collaborations. I want to write more proposals because it was so fascinating to get this data, but we need to demonstrate that it was scientifically useful to get the funding. It was a very challenging project to fund as well. It probably took like, I don't know, 6 years to get the funding for this because I was part of, I think, 4 failed NSF proposals. Eventually, they actually said the words too risky. I was like, yes, Keck. And then Keck funded us, but they only gave us, I mean, they gave us like $1.5 million without overhead, which sounds great, but it costs $3 million to run that cruise. And so the ship alone was $1 million for a month. And so we got NSF funding with a 60% budget cut because they didn't like our proposal that much. And so we cobbled together $3 million that way in order to make it happen. But we have very little money for analyses. So if anyone wants to work on stuff for free.
Real quick, any questions online that anyone wants to ask or comments or anything?
So for the multiple channels seismic data, and I know this can be used to, imaging the sedimentary structure, but I would like to know what's the contribution, of this data set to the study of the glacier.
So what we're hoping to do is, in that model that I showed that was this like glacier interacting with this substrate, those equations that link those two systems together are based on subaerial rivers for the most part. And so we want to link the actual ice dynamics, like velocity, elevation, the meltwater discharge to the sediment that's being produced in a set of equations. Via, we think, 4 different processes. We think there's glacial fluvial sediment delivery, there's mechanical pushing the sediment from the velocity. We think there may be freeze-on because there was that layer frozen on ice, and then that's melted out, and then there's diffusion of sediment contributing to loss of the sediment at the marine. And so we want to build these equations, and so the idea was to use the in situ ice observations at the time that sedimentation and diffusion are happening so that we can capture to the best of our knowledge what those equations will look like. Now we propose to go to 3 different systems that were behaving quite good, have very different ice dynamic behaviors. Either they've retreated a lot, they have retreated and stabilized, or they have different fluxes of discharge. And we were hoping to sample a wide like parameter space, but those were totally iced up. I think because of low winds, for some reason, the winds were lower the last couple of years and not blowing the launch out. And this one was more free. And so we ended up doing a lot more sort of time series analysis at this fjord. So, remains to be seen if they'll be successful in getting these sets of equations that we're hoping to get. But that's our goal in the end, was to try to marry the ice dynamic observations. A lot of people have gone and observed moraines in the paleo environment where you don't know the ice velocity, you don't know the position of the terminus exactly, you don't know all these variables that we're trying to capture simultaneously.
Basically just a couple of the ice dynamic model with segmental dynamic model.
Yeah, and that's like on multiple scales. So the idea in the NSF proposal that kind of failed to resonate with reviewers was that we would build nested resolution models. So one that resolved all the processes that we thought were important, and then sort of more coarser resolution ones that could scale up to the ice sheet level and taking the very basic information from those process level models up to an ice sheet scale where you could say, okay, it matters for this glacier, it doesn't matter for this glacier or this scenario or something. But that's gonna maybe happen, I don't know. We didn't get funded for that, so that's probably the next proposal to be written.
Awesome.